da di da di da da di da da di da di da da di da. What do you hear over the air?
Okay, good morning everyone, and I'm Veijo OH6KN, and come from the north, from the land of ice, Radio Arkala, and this is our virtual reality picture of Radio Arkala here, which we already did 2006, and so we have been in digital world already since quite some time, and actually there you also see the monster that is no more with us, so rest in peace. Okay, my topic is IoT, but actually I took 5G and cloud also as part of this, because they all go hand in hand. You can't talk about them without all of them three being in the picture. And there the, how does it work? Okay, yeah. Content, I first talk about the technologies themselves and what's the status of those, and that's my daily work roughly at Nokia, and then opportunities in ham radio. Then I have one update of one technology that I presented last year. It was not a cruise, it was on land, and then there's some progress being made which is important, and I want to show it to you, and then a conclusion. Okay, then when we look at 5G, this is slightly busy picture, and this is milliseconds and related to different things. When we start from like web page load, there are latency requirements, which is how fast the data comes over the network, or what is the time to come over the network. So it's like 150 milliseconds is fine. You don't notice when you press the button, then it loads and so on. Then we go further down. Sprinter, these good guys, their reaction time is about 120 milliseconds when they hear the bomb and then they start running. It's about 120 milliseconds. It's pretty fast, but in electronics it's a long time. Then when you start looking at that more newer technologies, later technologies, cloud-assisted driving. We have been hearing about autonomous cars, like Google Car and so on, that have been driving around California for millions of miles and so on. There you need about 10 millisecond delay so that you can get, for example, maps, or there's a warning or something. So it's getting quite short. Then when you look at some other things, like virtual reality, now we have virtual reality games coming up, and then they start to require fairly fast reaction time, so that you shoot something, then you want to see fast the feedback and everything, and that's 10 milliseconds or something. Then, okay, this is, I don't know even how to pronounce this, vestibulo-ocular reflex. That's something when you turn your head, then you want the picture to follow your eyes, the movement of the eyes, and that's, again, pretty fast, 7 milliseconds. If it's slower, then you start feeling that you turn your head and the world around you is too slow. Then when we talk about automatic electric control, it's about 1 millisecond time. Reaction time, I actually don't know why, but so it seems. And then high frequency trading today, these automated trading machines in stock exchange and so on, they are reacting at 0.25 millisecond. So someone makes money in 0.25 milliseconds, or loses money. And then when we look at today's networks, you take your whatever wireless LAN at home or something, you look at the delay, it's typically 25 milliseconds or so, and it's difficult to go faster than that, or find something faster than that. Then, but there are phenomena that require faster reaction or delays, and so something has to be done. Then when we look at some laws of physics, here's light propagation in optical fiber. We all know speed of light, which is 300 kilometers per second, and it seems fast. In this world, it's pretty slow. We would have to do something better. And the reason for this is that First of all, in optical fiber, the velocity factor is 0.6, like in normal coax almost. And then when we look at round trip time, so in millisecond it can go to 100 kilometers, which seems quite long. In 0.1 millisecond it can go 10 kilometers. And this means that this is actually becoming a limiting factor. For example, if you have some driving information in the US, you can't use it from Europe because then the round trip time would be somewhere between 10 and 100 milliseconds. So this speed of light is becoming a limiting factor for this fast communication, and this means that the information has to be close to you. So it cannot be in the Rocky Mountains in Google server. It has to be somewhere here close to Stockholm if you have your car driving in Stockholm. It cannot be even in Finland because it's too far away. So these are some important elements. Then when we look at the real-time contestation, when you want to hear your CW or you want to run QSK or something and remotely, then you need to have latency somewhere around this area. Then, by the way, it's I told to Björn that now Bell Labs is part of Nokia, and then Nokia has invented the transistor. We didn't know about that at that time, but we have done it, and it was fun to tell to Intel also that, by the way, we have invented transistor, what have you done? And then there's a famous guy running the Bell Labs, and he's called Mark Weldon, and I will pose him the problem that you need to invent something faster than speed of light, otherwise we will be in trouble. So there's a challenge for him. Okay, then the next one. Now this is 5G. This is sort of a general picture, and it has three key elements. One is high data rate, 100 megabits per second, wirelessly everywhere basically, and then peak rates up to about 10 gigabits per second wirelessly. And that's much faster than I think any one of you have at home. Some of you have this speed at home, but none of you have anything like this. Then I already mentioned the latency. Now the target is to have less than 1 millisecond latency, and that means that the communication can't go too far away either. And this is a real challenge. I think this is more doable somehow, but this is a real challenge because of this problem with the speed of light. Then third is this kind of a IoT type of thing, so that you want to have lots of, maybe billions of tiny sensors wirelessly linked to network. They need to have very long battery life, so small battery and should stay alive for 10 years. And that means that there needs to be a way of signaling and everything so that the communication doesn't kill your sensor, because typically communication is the most power hungry part of that sensor. So we need to invent some low speed way of communicating. Maybe the sensor will send once a day 1 kilobyte of temperature data or some other data. So all these three things are new, and they are sort of part of 5G. I think it will start from high speed, then it will go to this, and then the last part of the standard will be related to the IoT. All right, I had this remote here. Then how we would get to 5G? There's sort of a roadmap, and Björn comes from our dear competitor. He knows it very well also, and we both have been promoting this kind of a roadmap together with Ericsson, so first is 4.5G, and it can be done using today's base station hardware roughly. Not every phone will support it, but some of them start to support it, and it's coming quite fast. Then some Pro, so gigabit per second speed in good case, and some maybe 10 millisecond latency. 4.9G, maybe in 2020 or something. This can require new hardware, so higher data rates again, lower latency. And then we go to about 5G, and again, higher speed, lower latency. And then when we look at the schedules, this is, now we are working on trials. So there are trials around the globe, but they are very sort of rudimentary trials. The first big show will be Winter Olympics in Seoul, the land of Samsung and those high-tech guys, and so it's already next year, and I think in February or something, March next year, and then there the target is to show 5G capabilities, real-time video when someone is doing downhill or something, that kind of things, and the companies are working big time to get demonstration systems and sort of pre-commercial systems in Seoul. So there will be Winter Olympics. Behind the screen there will be Telecom Olympics, and that may be even more fierce game than the Olympics themselves. and then maybe around 2020 or 21 or 2 or so there will be commercial launches then more broadly. And it's also good to understand that this 5G will not replace 4G or these guys. It's an overlay, so both will exist, and this 5G may not be available in rural areas, maybe mainly in towns and so on, so that it's not either or, like 3G has been mainly replaced by 4G, LTE and so on, but this will be overlay on top of 4G. All right, then go to IoT. This is simple structure of IoT. I mentioned sensors. So this can be high-speed sensors or low-speed sensors. High-speed sensor is typically a camera that is doing some surveillance of whatever. Or low-speed sensor may be a temperature gauge somewhere on the sea, sending temperature once per hour or anywhere. Then you typically have some kind of a gateway, so it's collecting data from these sensors. Then the gateway has higher speed communication through the network. Then we have cloud, which is collecting the data. And then now we have this big data. People have been hearing about that. So it's a collection of the data of sensors, then doing some analysis, and then can do some machine learning. So can find some patterns there, maybe some alarms or something could be found. And then there are applications that are using the data. So, and this is basically existing. The cloud is clearly existing. There are big data centers around the world and growing fast. Machine learning type of things have been there, but not very strongly yet because the algorithms are very difficult and consuming. Then these sensors and gateways, these are not very broadly used yet, but fast. They are growing. The number of them are growing fast. Typically, like you take a factory, lots of sensors, but they are wired. With the IoT, you could go wireless with the sensors, so cabling, everything is much simpler. And then, of course, some applications. There start to be applications using, for example, machine learning. This Watson, IBM Watson is a good example of that, and so on. Then, when we look how it looks in reality, it looks like this. So we'll have the sensors. We have some technologies that are low speed, short distance, like Bluetooth, Wi-Fi. Okay, it's not low speed, it's quite high speed, but still like a couple of tens of meters. ZigBee is another technology. LoRa is quite interesting. In France, it's countrywide. In Finland, it's becoming countrywide. It's low speed, a couple of kilobits per second, but it's using 430 megahertz or something. So it's within the 70 centimeter band. And so it can be quite long distance. With 1 watt, you can go maybe 100 kilometers. So there's another technology. Then you have gateways. For example, phone can be a gateway. It can take the Bluetooth signal, then send it to over data, 3G or 4G to network. And so you have gateways, and then you have network. There are typically the cellular standards. Maybe Wi-Fi can be also seen as a network for sure. Then there's some management type of things like security control, and configuration and everything. Then there are applications. And these are sort of so-called vertical. So, for example, healthcare will become very big user of so patients can have wireless sensors somewhere or heart sensor or something. Then there's a healthcare application following your heart rate and everything, and you don't have to stay in hospital a long time and so on. And then big data and analytics is part of this. There are challenges. This tends to be okay today and so on, but then when we look at the low levels, it's very fragmented. There are no standards for this, or there are many of them. Interoperability is not good, and so on. So there are sort of proprietary applications there. Security is another one. This is pretty much secured today, but if this is not secured, the data coming from here to here is not secured because there's a weak link somewhere here. So security is becoming very important, and people haven't realized that. And there's one good example from the US, which is a true story, that there's a security company selling security services and selling security equipment. And so you install expensive security alarm system in your house, and it had a hole. It had a security hole. So people could hack into the security system, disable your security, and empty your house. And that was not good reputation for the security company itself. So, and they failed, so that they had wireless sensors in windows and infrared sensors and so on in home, and people could hack into that communication. It was unsecured communication. Then the rest didn't matter. Then, okay, going to ham radio, how this is going to impact us. And then first I start from this kind of architecture picture. This is a picture that I showed last year, except I didn't show this cloud and 5G here. So I had internet connected, and so it was this multi-operator 100 radio. It can be 200 radios, it can be 50 radios, but it's definitely more than SO2R or so. And then so you have SDR transceivers plus PAs. You can have just SDR receivers as multiplier receivers here. Then, of course, you need some antenna relays and rotators and so on. And all this can be then controlled from your PC. Maybe you have this kind of a flex, what is the remote head called, so that you have a couple of knobs because you want to spin the VFO rather than mouse or something. But these, you can have as many as needed, as long as the capabilities of these guys will be enough. And basically, I mean, the rules say that this should be within 500 meters. The rule doesn't say that these guys have to be within the 500 meters. Or maybe it's bending of the rule or something, but you can be at your home and so on. So you can have this kind of virtual multi OH2U. Not just the antennas are at OH2U and the guys are in Helsinki, in wherever. Then, so this was picture from last year. And then now I've introduced the cloud, I've introduced 5G here, so communication can be over 5G. Of course, it can still be over the internet, but if this is slightly remote place like Arkala, I can't get 100 megabits per second fiber there unless I pay 50k euros. And I don't have 50k euros for my optical fiber, so something faster has to be gotten there, and then the 5G should be the promise. Then all the applications could be here in the cloud, so you don't need basically this could be just a web server, a web browser. It's a user interface. Then it can hide everything, so you have different models here, but the cloud can sort of abstract all the hardware and all this. So this is a future architecture, and how many of you are working on this? Hands up. Yes, I know Björn is working because of your work relationship also. Yeah. But it's good that there are people working on this. Yeah. Yep.
Do you think in the rural areas we will have 5G?
That's a good question. I think in some areas there could be, but you never know. But for example, Arkala is along one of the main roads, so there we believe that we could have 5G. It's a couple of kilometers away from one main road. But it is true that 5G will not be there, and in rural areas, maybe even not LTE has been installed, so there are problems there. And then if you think that the station is somewhere on a Pacific island, there's even less of 5G on the island. Yeah.
How much of the data processing do you do from actual?
Yeah, that's also a good question, that how much processing is done here and here. So it makes sense, of course, to have the basic SDR functionality there, but whether you do demodulation here or in the cloud is another story. If you don't do the demodulation here, then of course the data rate is quite high to the cloud. You send the IQ data like a couple of 100 megabits per second, which is quite fast, and then you can do the demodulation here. Or if you do it here, then basically it's only audio and you don't need that much work in the cloud. It is, yeah. 4G could do something, like at my summer place, which is supposed to be a remote place, but I have 40 megabits per second, unfortunately, so I can do some work also from my summer cottage, and can run video conferences and so on, but yeah, it depends. Then there are some use cases, new use cases. Like mentioned, that your station can be in a good location, so especially in urban areas where you don't have space for antennas, you have a lot of QRN or man-made pollution on the spectrum and so on, so you can have stations in good place, like club stations could be there. Arkala is a remote station, and then we have a good example of this remote ham radio where you can buy time in the US, so you can rent a station, and those tend to have good antennas. It's, I don't know, was it like $0.50 per minute if you want to run low power, and then it's $1 per minute rent if you want to run with the amplifier. But this is very popular in the US. I know quite a few guys who mainly do DXing through this remote ham radio, but this is commercial one. But if you have a club station, it's just for the club members and so on. Then already showed this separation of the operation positions and physical station, and so virtual multi stations, they are the future, or this technology allows them to be there. Then a new de-expedition model. Basically we could have an automated station somewhere, maybe even on PS7. So just land a module there, leave it there, solar batteries, antenna, it's a box. And of course you would need the communication channel for that. Maybe it can be done through satellite. It's not that high speed and expensive and so on. OH2UA is working on this kind of a shortwave data communication system, so maybe Tony needs to deliver some data communication to Scarborough and so on. But yeah, this can be done. And whether people think that this is real de-expedition or not, but at least the station is there and you can make contacts from a real location. There are lots of places that it's easy to have. There's electricity, and then you can get there and so on. So this would be a poor man's model for de-expeditioning. Then when we look at the IoT part of it, so wireless ham shack, no wire connections basically, not within the ham shack, nor to your towers or something. Radios can be close to antennas, maybe a box just below the antenna. You don't need a big ham shack. You have a couple of towers, then you have some cubic meter of box. In Arkala needs to be heated and so on, but you don't need to anymore have sort of a ham shack there, and no long cabling. Or with Tony OH2UA we have been sort of innovating that we can put the radio to antenna. And for example, if you have a stack, you could have SDR per antenna, then you could do beamforming or this beam steering electronically, and the radio can be right at the antenna. Of course, when a lightning strikes, then the radio has hard time. Okay, then these three things, cloud, 5G, and IoT, what they can do for ham radio. I think that basically, I would think that the cloud probably is the biggest thing. And yeah, I'm sort of saying that it could be universal, somehow standardized open source platform so that you can extend it as you wish and so on. Doesn't cost anything. Have a community to develop it and so on. So platform for the whole MO100 radio. Or same thing for DX station. It doesn't make any difference whether it's a contest station or DX station. Of course, the requirements for contest station are tougher because many stations are more real time, but DX station can use exactly the same cloud-based platform. And then I've sort of divided into 4 categories how the cloud would be used. So radio management, like in the picture, I had the radios, and we discussed already whether the SDR algorithms would be in the cloud or in the radio. It can be both. And when they are in the cloud, then it's easy to update everything, and you don't have to have any software in your PC or something, basically. Multi-user control, this multi-operator, 100 radios, you have 25 operators. So how to control those, synchronize them. Hardware management, it can be abstracted, whether you have a Veijo, whether you have ICOM or Elan or Flex or something. It looks all the same because it's abstracted. So you don't need to learn different knobs or menus, basically, or so on in ideal world. Then this data management, this is probably maybe the most important one. So log management, if you have multi-operator system, then the logs have to be real time. These can, when they are in the cloud, then they are synchronized automatically. You don't need network between the PCs or something. Real-time logging, and this is actually sort of I think it's part of the overall. Then tube sheets, very easy to create, and they can automatically, this can go to whatever LOTW or CQ worldwide contest pages directly, so that every QSO you make then goes already to the log checking. Real-time scoreboards, we start to have these, but when log is in the cloud, then the scoreboard can be automatically done out of that log data. It can be global. Every contester is in the scoreboard. Then big data analytics. We can, when we have a lot of QSOs, for example in LOTW, or we have this what is this G7 log, club log, yeah. There you can see that when people have made QSOs to K5K on 10 meters, you can see from the previous QSOs that what is a good time to be there, and so on. So propagation could be easily driven, or propagation data could be easily driven out of the big data of logs, of QSOs. Log checking, simple to do. Rule bending, so quite easy to do. Also, when you see Summit introducing some multipliers, you can right away see that if people have been using it and they go and work it. So that could be automatically easy to do. Then if you do recording, then of course you can listen afterwards, or you can do automatic analysis that there have been 2 transmitters on at the same time, or if you're a single operator and you are running 3 bands simultaneously, it's not very easily doable. RPN type of things, simple to do also. Then we look at voice and communication management category. So voice has to be routed, maybe have to be decoded, or in any case has to be transcoded or something, coded, recorded, and maybe transcoded. Recording of the for log checking and for your own purposes. And this is being done, but it's being done at one certain particular spots, and then you have a hard disk, and then you analyze it somewhere. This data can go directly to the cloud. spectator service, so you can listen to the stations. If you include video, then you can also watch the operators, so it is fun to watch. Then social interaction, we shouldn't forget this. When we go to a location, to a building, multi, it's fun to be there because you see your buddies, you can have beer, you can have some fun, and so on. But sometimes you have to drive 300 miles to get there, and so it's not always so easy. So you can have virtual teams, you can have this kind of chatting, cheering, everything. You could have virtual beer somehow. Yeah. All right, so yeah. At least this is something the cloud could help us. Then the 5G part. And of course you can go to a certain place, but then still you could use the virtual station. Then the 5G itself, it's a fast data pipe. And so what it could do, of course, wireless connectivity, which is important, real-time capability. I showed you the delay and latency things. So basically you can run your station so that you can listen to your side tone, or if you run QSK, you can hear the receiver in between your transmits and so on. You can listen multiple radios quite easily. You can have as many waterfall displays as you can follow. People typically have 2 ears, so maybe the audio still could be mixed from a couple of radios and so on. Spectrum displays are simple, and then everything is IP based. So it doesn't matter where it is, the IP routing will take care of it. So abstracting the physical instance is easy when everything is IP based. For example, in Arkala, I did the original plan so that there are relays like at the bottom of the station. There are lots of relays in the ham shack, about 400 or 500 relays in the ham shack and so on. I was thinking that every relay has an IP address. So when I put my antenna on 20 meters, I just send a set of IP addresses and turn on. I didn't do it because I was afraid that lightning will kill the processors at the bottom of the tower. So now there are hardware lines or physical lines going there, but there's I think about 60 wires per antenna. All is just relay control and potentiometer control and so on. So that's old-fashioned. It works. But if I just would have one network, I just send IPs and there my 20-meter antennas come on, if things work. Then looking at the IoT, so we could have standardized wireless interfaces, so no different kinds of connectors. And then, like I said, that they can be placed globally. I could easily run OH0X-ray from my home, like I run OH8X-ray today. I can't run OH0X-ray because we don't have a system for this. So all of these can be wirelessly connected, and again, they have an IP address. And wireless ham shack, no cables. At least in Arkala, it would be a dream come true, because I just can't move somewhere because there are so many cables, or if I go there, then I break something because I step on a cable or so. It's a nightmare. Coaxes you still need to do. You can't run a kilowatt over Bluetooth or something. So those you have to have, and then 380 volts or 220 volts. And then these things are available. There are good IoT platforms, but like I said, that they are not standardized. And these are some examples of this. Embed is one driven by ARM, a UK company. Arduinos are very well known, and they are sort of hobbyist cheap platforms, and they can have wireless connectivity. Raspberry Pi is a cheap, good platform, can run Linux and quite demanding applications on top of it. And there are more of them. And many of them nowadays they have support for the cloud. It's not so easy to set up this, how to send data to cloud, some application, Amazon Cloud or something. But the software running on top of these guys, they already have support for the cloud, so it's quite easy to set up your data path to cloud. Then with your tablet or PC or phone, you can look at the data quite easily. So I've seen lots of demonstrations where it has been set up in 10 minutes. Of course, you need to know how to do it, but it doesn't take that long. Then, I'm proposing that harm, there's a mistake. Ham radio class for the IoT. Sorry about that. So that there could be a separate class of like I said, that open source standard or something. Then we have all radios and rotators and that kind of things defined there. We could have this kind of a standard interface between the hardware and the cloud, and things would be easier. Okay, this is roughly most of the topics here. Then there's a picture. This is actually an old picture. I think I presented this in Friedrichshafen a couple of years ago. So we are not the only ones needing this kind of remote control. So this is showing, I think this is from Australia somewhere. These are telescopes somewhere in a good place. Not in town because you have a lot of pollution, light pollution and so on, or you may not have space. So this is somewhere in a good place. And I know in Chile, on the sort of a high plateau of Chile, there are lots of big telescopes, but there are also hobby telescopes there. So there's a set of PCs controlling these, and you can control them remotely. And this was a couple of years ago, and at least in Chile, I think it's commercial service, so that there are people who live there. When your PC stops, then they go and boot it and so on. So you have to pay some price for the maintenance, but not that much. And then a lot of US people have telescopes in Chile, in good location. Then when you link this to the cloud, if all the pictures of the telescopes go to the cloud, then there's big data analytics of those pictures. That may be a more powerful way of finding new stars or something in the space, rather than looking at the big Hubble telescope that can only watch one person, one direction per night or something. So these can be much more powerful. This is sort of crowd-based star finding or something. And if there are thousands of these guys, then it can be much more powerful. I'm not an astronomer, but this looks quite fascinating. They have exactly the same problems: light pollution, signal-to-noise ratio type of things. Beam width is narrow, and so on. So very similar to radio stuff, just a different frequency. Okay, then I promised to show one technology enabled by digital processing, software-defined radio, and this is a picture from my last year's presentation, and now I'm focusing on this guy, so-called digital pre-distortion, which is now used in base stations a lot, cellular base stations, for good reason. And this is simplistic view is that you have the digital signal being done digitally, processed here, then you have D to A converter, then you have your PA, then it goes to the antenna. But then you sample with the A to D converter your output here. And by the way, this can include your whatever tube amplifier, LA4000 included, and or a solid state amplifier, 1 kilowatt or something. So you sample at the output of the whole transmit chain, not the output of your transceiver or something, but the whole output chain. And when you sample this and you see spectrum spikes, like spurious or harmonics or something, or splatter, which is very common, at least coming from the signals from the east, across the border from Finland, and so on. So then when you sort of listen to your own signal, you can start pre-distorting your signal so that it will dampen or push lower your splatter or your harmonics because you listen your own signal. So you can do it, and there are algorithms, simple ones and complex ones, and that can do it automatically. So it can improve your rejection, two-tone rejection or IMD rejection from about 30 dBs from carrier down to about 50 or 70 dBs. 50 is a typical figure, 70 would be a perfect figure. And when it's 70 dBs below your carrier, I mean, you can't hear a splatter 1 kilohertz higher or lower or something. And so, for example, 40 meters would look much nicer also on SSP if we all would use this kind of technology. And then this has been in use in commercial solutions like base stations and so on, but not that much in ham radio. Then next picture is showing here. First of all, this is a good presentation by Warren NR0V. He did this presentation in Friedrichshafen. And this is a station using this, I need to check this. This is HP SDR, this high performance or whatever SDR. I think it's driven by this TAPR, this Tucson Amateur Packet Radio community, which is very technical community. They have this SDR solutions as modules and so on. And now this is a 1 kilowatt station with some transistor amplifier, and this is basically SSP without any DPD technology. Now this is with the DPD technology, so you can see that the IMD went from 30 dB to about 50 dB, and this is getting to be a clean signal compared to this. And this is not even splattering badly, so this is simply pure signal. If this would be splatter, then maybe it could be the skirts would be somewhere here. If you clean them, then basically with a good receiver you can't hear if it's like 1 kc off or something. And if everyone would have this kind of technology in use, like that 40-meter SSP would be a joy to run in CQ worldwide, like it's not today. And I know that there are radios that use this. For example, this Elan SDR, it has this, and it has been named at least this technology that is coming from this organization. It's called Pure Signal. So this Elan can support this Pure Signal. You can feed the power amplifier output back to the Elan SDR, and it can do this cleaning for your signal. Flex, I don't know. Flex should have it. It's coming, yeah, and so on. And it doesn't matter what kind of amplifier, whether it's tube amplifier, whether it's LDMOS transistor amplifier, and so on. It's just sampling the output and then pre-distorting the input signal there and cleaning it up, and it works. And this looks magic, but it works. So that's one thing that has changed over the last, I would say, a year or two, so that these have come and people have proven that these work, and these should be used much more. If you have SDR, then this technology is simply simple to implement there. It's more software, more algorithms, but very doable. If you have Yasu 5K, like I do have, you can forget this. I'm more in this range with my Yasu or iCommerce, so it's not only Yasu problem. All right. Then to conclude, clearly, it's clear that this IoT, 5G, cloud will change the world pretty much, and ham radios, they used to be in the forefront of new technologies. Now I think we are in the back front somehow. We haven't been following this too much. This multi-operator 100 radio station, which I launched last year, now I want to cloudify it, so that I put everything into the cloud. And actually we start working in Arkala somehow. This big work and so on, we have some ideas what to do and so on. First make things web-based. Today they are not web-based for remote. That's the first step and quite doable step. Then the next step is that maybe we have more in the cloud and so on. Then I presented this key user planes, this radio plane, data plane, audio communication plane, and social interaction plane, including beer. Then I didn't address this hemisphere, which is one application of cloud, so that you simulate the whole radio propagation. You can send CQs and everything, and you can work stations in hemisphere without any license needed, without any radio needed. And Martti organized a contest, WRTC hemisphere, I think it was last year in Finland, and then when he was not in Pacific but Caribbean, so he was promoting hemisphere and so on. So that's one application there. I didn't touch it because that's a different story. But they can also benefit from these technologies. Okay, any questions?
That CQ serenade.